Okay, so we are on page 154. So yeah, you were asking about craters within craters.
It's on.
Nice. Here is a crater, and when a large body impacts, it shoots up a lot of material into the there's no atmosphere on the moon, but into the sky around where it hit. And that material that it shoots up is super hot. So it's liquid. And it forms beads. It forms perfect spheres. And then those perfect spheres fall back because they get cooler and they harden. And so you see a lot of that on the moon, these little spheres here. And if you look at the spheres up close under a microscope, you'll often see little craters on those too, of microscopic particles that are constantly bombarding every object in space, and they form little microscopic craters on the seemingly smooth surface of these little things. So the cratering is, the amount of cratering is huge. I mean, there's craters on top of little particles that come out of craters. Crater's just a fun word to say. We don't have nearly as many on the Earth because we have an atmosphere. And a lot of the particles burn up as they enter the atmosphere. They never reach the surface. But on the moon, there's no atmosphere to stop anything. So they're constantly being hit by particles. Even now, there's little things hitting the moon. Most of those particles burn up in our atmosphere. Due to impacts, there is a dust produced that will cover the moon over time called regolith. The entire moon is covered by dust. And it's from impacts that shoot stuff up in the air, and then the dust settles. And so when you see the guys walking around on the moon, they have to move kind of like this because it's hard to just walk regular on the moon because it's so light. They're constantly kicking up dust. When you film that, are you even like looking at, is it just in one location?
I can turn if you want me to.
Yeah, you probably need to turn it to show the people what I'm showing up here. So the regolith will slowly cover up small craters and smooth the edges over time, which provides a way of dating craters. If the edge of a crater is real smooth, because it's got a bunch of regolith on it, that means it's an older crater. If the edge of a crater is real sharp, not much regolith has been deposited over it, it's a young crater. And so there's a science to dating craters that way.
What does BYA stand for?
Billion years ago. We know that the cratering rate really dropped off about 3.9 billion years ago, which we take to be the end of the formation of the planets. There were a bunch of craters impacting the moon, and then about 3.9 billion years ago, it kind of stopped. And after that, ever since then, there's been some cratering, but not nearly as much as there used to be. So when we look at the formation of the solar system, we see that it kind of was pretty much done forming by about 3.9 billion years ago. All the debris that was floating around the sun had either coalesced into a planet or had been knocked off into deep space. There's an astronaut running around on the moon, and you still see shows today like, oh, the moon landings were a hoax and this stuff, and they got all this evidence, which is completely ridiculous. You can see with telescopes now the stuff that's on the moon. They have telescopes so good that you can see a footprint on the moon left by an astronaut. And all that stuff is still up there. including all the equipment they set up to study moonquakes and things like that. And there are satellites going around the moon right now mapping the surface, and those satellites have good pictures of the vehicles and stuff that the astronauts left up there. And plus they brought down 900 pounds of moon rock that how would that have gotten here?
Teleportation.
It couldn't have come through asteroids, because when a meteor comes through the atmosphere, it heats up, and that changes the structure a little bit. And all the moon rocks don't have that heated structure. So all those shows and things that say the moon landings were a hoax are just ridiculous. It's just made up stuff, and people still watch it and believe it, and it's just crazy. People are crazy. You can see the tracks. That's one thing that you can really see well from those satellites, is the tracks that the rovers left. Those will be there for millions of years until they're eventually covered up by that regolith dust. Wouldn't it be fun to go to the moon? Only 12 people have ever done it. They're all Americans. That's cool. What about the magnetospheres? Anytime that you have a moving bunch of metal moving around, you'll create a magnetic field. And that's exactly what the inside of the Earth has. Moving metal that swirls around, liquid metal that swirls around. It's our outer core of the Earth. And this rotating metallic core produces a magnetic field around the Earth. The Van Allen belts are field lines which extend into space, along which charged particles traveling in space are trapped. And this is a cool picture of what our magnetic field looks like. It extends way out from the Earth. And these little lines that you see here are magnetic field lines. Have you, in physics or physical science, did you take a bar magnet and shake little iron filings around it? Did you? A couple of y'all are nodding. And it forms little lines around the bar magnet? Yes?
What'd you say after particles?
Charged particles traveling in space are trapped. Got it? Well, the same thing happens with the Earth. And the magnetic field extends way out from the Earth. And the solar wind that it's showing right here are particles coming off the sun. Protons and electrons. Charged particles that are deflected by this magnetic field. The magnetic field deflects all charged particles. And so some of the charged particles are deflected above the North Pole and some below the South Pole and kind of go right around the Earth. If we didn't have these magnetic field lines, we'd be bombarded by these high energy particles from the sun, and those will kill a person or any living thing over time. So if we didn't have a magnetic field, there wouldn't be life on the surface of the Earth, at least. Maybe down in the oceans, because water blocks the particles too. But not on the surface. So it's good that we have a magnetic field.
Doesn't that stuff like destroy computer data?
The solar wind particles?
Yeah.
It can if it gets down to the Earth. Now usually it doesn't, because the magnetic field blocks it. But if the solar wind is especially powerful, which happens on 11-year cycles that we'll study later, has to do with the sun. But sometimes really powerful solar blasts can make it all the way down to the surface. And even this magnetic field doesn't block it. If you look at the way the magnetic field lines work, they curve around the Earth from pole to pole. And they actually curve back into the Earth at the North Pole and the South Pole. And so particles that hit the magnetic field will curl, go in little curlicues around these lines, and will actually come into the Earth at the North and South Pole. And these particles hit the atmosphere at the North and South Poles, and they hit it so energetically that light comes off of the atmosphere. The atmosphere absorbs the particles and emits light. And you know what we call those lights in the North and South Poles? Oh, the auroras. The North Pole is called the Aurora Borealis, and the South Pole is called the Aurora Australis. The Aurora Borealis are the northern lights. You ever heard of those? Produced when the charged particles travel down the field lines and enter the Earth's atmosphere. I got pictures of those. Ah, there's the northern lights. You can't see them unless you get up to go up to the north, near the North Pole, like Alaska. You can see it really well. I mean, these things. You're getting it almost every night. Some nights it's real bright, and some nights it's not hardly there at all. But it just depends on the solar wind activity coming off of the sun. Look at that. That's a picture of the sky near Alaska there. My dad drove up to Alaska to see them. Said it was pretty spectacular.
Is that in Alaska too?
It's up there somewhere, yeah. I'm not exactly sure. Supposedly beautiful, and you can just go watch it. Ooh, look at that. That's a great picture. Let's see what this says about it. Oh, this is lame. Terrible. Why even show that, Mr. Rosenberg? Sometimes the activity is so great that the lights will spread downward. And they've said to have been seen as far south as Florida in history, but I've never seen them down here. Usually you have to be at least up in Maine or so.
I know people that have seen them in Michigan.
In Michigan?
Yeah, but
Nice.
I remember.
Yeah. That's a good comment, though, Ellen. It's a comment deserving of the bathroom. Yeah. In southern Australia, yeah, you can see the southern lights. Antarctica, the tip of South America, down the southern part of Africa, but you usually don't even see it in those places unless it's really active.
They look the same as northern lights?
Yeah, it's just the sky lit up. It gives off all kinds of colors.
Sure, upside down.
Then finally, oh, by the way, the moon doesn't have a magnetic field, just the Earth, because the moon has no swirling liquid metal. So you don't get that unless you have moving metal. And the moon just too cold, it doesn't have that. So how did the moon form? They know through all sorts of experimentation that it must have formed from a collision. What happened was the Earth was hit by another large body in space, probably a body the size of Mars, another planet, came and impacted the Earth very early in the Earth's history. We're talking billions of years ago, just after the Earth had formed and started to cool. There's another planet kind of near the Earth, and they're going nearby, and they get closer and closer, and bam, they hit about 4.5 billion years ago. And it blew off huge chunks of material from the Earth that eventually came together to form our moon. And we know this for a lot of reasons. The surface of the moon is very similar to the surface. The compounds that make up the moon's crust is very similar to the compounds that make up the Earth's crust. And that's similar. It's too similar for the moon to have come from somewhere else. It has to have been part of the Earth at some point. So it was probably from that rogue planet that impacted the Earth and became part of the Earth and also became the moon. And they show kind of a step-by-step analysis of how this forms. And I have it here on video. This is a pretty cool video showing.
Planet Earth at the beginning, 4.6 billion years ago. Its surface erupted in a sea of molten magma. Later, the planet was in the midst of a slow cooling process. Vapor rose to the sky, condensed, and fell to Earth in a torrential downpour. In the aftermath of the seemingly endless deluge, the primordial ocean was born. The atmosphere after the formation of the ocean was heavy with carbon dioxide, much like the planet Venus today. Earth was sealed off by thick clouds, and the lone streaks of sunlight that penetrated the cloud mass tinted the sky orange. Earth was like a giant steam bath with ocean temperatures soaring over 300 degrees Fahrenheit. But in this primordial soup, the building blocks of life were accumulating. Meteorites showered the Earth, perhaps bringing amino acids necessary for the formation of life. And then one day, 4.5 billion years ago, an asteroid the size of Mars collided head-on with Earth. This giant impact was the greatest event in our planet's early history. The impact was of such phenomenal magnitude that it carved out part of the Earth's mantle and hurled it into outer space. A portion of the torn mantle was drawn back to Earth. The fragments of debris scattered into space were swept up by powerful gravitational forces. They formed a new satellite, which would eventually circle the Earth. This was the birth of the moon.
Pretty cool.
So do they know which place was the part that got hit?
Well, that impact would have released so much energy that the entire Earth would have been molten again. And you would have had just a lava Earth, the entire Earth. And so all that molten stuff mixes together, and then the outer part of the Earth cools to form the crust again. And so there's no particular spot where it hit. It's rearranged the entire planet. That was way before there was any life or anything like that. So this is probably what the moon looked like 4 billion years ago, shortly after it formed. Still had a lot of craters and stuff because there were impacts. There was a giant crater there. That impact almost tore the moon apart. If it would have been much bigger, it would have completely rearranged the moon. Then the big craters fill in with lava, so about 3 billion years ago it would have looked like this, with the Maria having formed. Now it looks like this today. So, there's one of the big craters. Look at this ejecta. This is all ejecta on the side. These concentric rings right here are mountains. Mountains the size of our mountains on Earth. That little shadow there is a shadow of a huge mountain. These are big formations. So you read the last section there. 5.7, 5.8. Tomorrow, lab, we're going to set up a solar system, what's it called?
Wait, what chapter is this?
5. Test is over 4 and 5. We're going to set up a scale model of the solar system tomorrow out on the soccer field. Blow your mind. And then Monday we have astronomy, and then Tuesday's a test over 4 and 5.